Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of basic mechanical engineering. We'll dive into key concepts like types of fluids. Slide 1. Classification by physical state. We begin by categorizing fluids based on their physical states: liquids, gases, vapors, and plasma. Liquids are nearly incompressible with definite volume. Examples include water, used in cooling systems. Gases can expand and are compressible. Think of air in pneumatic systems. Vapors are gaseous forms of substances, normally liquids at room temperature, such as steam, essential in steam engines. Plasma is ionized gas, like the kind inside neon lights, and is used in higher energy applications. Understanding each state is crucial for designing engines, HVAC systems, and electrical devices. Slide 2. Ideal vs real fluids. An ideal fluid is a simplified model with no viscosity or compressibility, useful for basic flow calculations. A real fluid, like oil or water, has measurable viscosity and can slightly compress under pressure, more realistic for engineering design. Ideal fluids flow without resistance. Real fluids experience internal friction, leading to energy loss. Air at low speeds can often be treated as ideal, but hydraulic oils require real fluid modeling for accuracy. Recognizing which model to use helps engineers efficiently design pumps, pipes, or ducts. Slide 3. Newtonian vs non-Newtonian fluids. Newtonian fluids maintain constant viscosity regardless of how fast they flow. Water is a classic example. Non-Newtonian fluids, like ketchup, change viscosity under stress. Ketchup thins when shaken and thickens when stable. In Newtonian fluids, shear stress is directly proportional to shear rate. Non-Newtonian fluids do not follow this simple rule. Categories of non-Newtonian fluids include shear thinning, like blood, and shear thickening, like cornstarch in water. This distinction matters in industrial processes such as mixing, pumping, and food production. Slide 4. Compressible vs incompressible flow fluids. In compressible fluids, density changes significantly under pressure, common in gas pipelines or jet engines. Incompressible fluids, such as hydraulic oil, maintain constant density, simplifying analysis. Compressible flow requires Mach number considerations and complex mass conservation equations. In hydraulic systems, the assumption of incompressibility allows for simpler and accurate force calculations. Slide 5. Homogeneous vs heterogeneous fluids. Homogeneous fluids have uniform composition. Ethanol dissolved in water is evenly mixed. Heterogeneous fluids contain visible different phases, like oil droplets in water, which may separate over time. Homogeneous fluids flow predictably, while heterogeneous mixtures can settle or clog pipes. This difference is key in processes like water treatment and food processing, where separation and mixing matter. Slide 6. Summary and importance. In summary, fluid types vary by state: ideal, real behavior, viscosity response, compressibility, and mixture uniformity. All categories have practical engineering significance. Liquids and incompressible fluids in hydraulic systems. Gases and compressible fluids in aerodynamics. Non-Newtonian fluids in food and chemical industries. Heterogeneous mixtures in environmental engineering. Identifying each fluid's type helps in selecting appropriate models and equipment for analysis and design.